All right. Time to get ready to go. Let's see. What am I hearing? Something about the mic is like really... It's really, what's ringy? Test, test. No, is that it? It's so weird. All right, I'm hearing it from here, I think. Yeah, I'm hearing it from Q1. I don't know if this is coming across in the recording, but it is very ringy. All right, not entirely sure. Everything else about it seems fine. I don't have any weird effects going on. I'm going to try and turn this off and back on again just to see if that fixes anything. All right. Is that any better? No, it's the same. Test, test. I didn't have this yesterday. All right, well, I'm just going to get started. I'm not quite sure what's happening with this ringing I'm hearing, but hopefully I'll figure that out later. Okay, we're gonna do day 8. I actually came across a really cool crate in the Rust ecosystem called AOC Runner, and I thought this was pretty cool, and I wonder how much of this we could maybe replicate in Swift, where you can add some metadata to a file, and this is like a compile time macro. And then when you annotate your method with the day and the part, it will automatically put in the input from the program. Sorry, from Advent of Code, which I thought was really cool. And then there's a way to pre-process input, so you can get a generator which will take the input and you can turn that into something else and use it. I thought this was really cool. And then there's a way to run it. So this has a cargo extension called Cargo AOC. And then you can store your Advent of Code token. And then when you run it, you would say Cargo AOC, and it'll just run all the different parts. And it will also benchmark it for you, which is really cool. Some of this is Rust-specific tooling. All right. Yeah, some of this is Rust-specific tooling, so I don't know how much of this we could actually replicate in Swift, but I do like the overall idea. Anyway, all right, so we've got day 8. Let's open it up. Yesterday I finished day 7 and day 6 part 2. Test part 1. Let's go ahead and read the Advent of Code Day 8. You find yourself on the roof of a top-secret Easter Bunny installation. While the historians do their thing, you take a look at the familiar huge antenna. Much to your surprise, it seems to have been reconfigured to emit a signal that makes people 0.1% more likely to buy Easter Bunny brand imitation mediocre chocolate as a Christmas gift. Unthinkable. Scanning across the city, you find that there are actually many such antennas. Each antenna is tuned to a specific frequency, indicated by a single lowercase letter, uppercase letter, or digit. You create a map, your puzzle input of these antennas. The signal only applies its nefarious effect at specific antinodes based on the resonant frequencies of the antennas. In particular, an antinode occurs at any point that is perfectly in line with two antennas of the same frequency, but only when one of the antennas is twice as far away as the other. This means for any pair of antennas with the same frequency, there are two antinodes, one on either side of them. Okay, for these two antennas with frequency A, they create the two antinodes marked with a hash mark. Adding a third antenna with the same frequency creates several more antinodes. Two are off the right side of the map, so instead it only adds 2. Okay, so how does that one work? Does it reflect? No. Adding a third antenna with the same frequency creates several more antinodes. It would ideally add 4, but 2 are off to the right side of the map, so instead it only adds 2. It's kind of weird that they just said a third antenna, but there's another antenna here. So there's 4. Oh, sorry, I'm thinking of this backwards. The signal only applies its nefarious effect at specific antinodes based on the resonant frequencies of the antennas. In particular, an antinode occurs at any point that is perfectly in line with the two antennas of the same frequency, but only when one of the antennas is twice as far away as the other. This means that for any pair of antennas with the same frequency, there are two antinodes, one on either side of them. So is that because of the distance here? They're like one away diagonally, and so those are also one away diagonally. And when we add a third antenna here, we get this one on this side of it. This one's off map. And then I don't understand how they got this one. Oh yeah, this one. Okay. Antennas with different frequencies don't create antinodes. A and A count as different frequencies. However, antinodes can occur at locations that contain antennas. In this diagram, the lone antenna with frequency capital A creates no antinodes, but has a lowercase a frequency antinode at its location. The first example has antennas with two different frequencies. So the antinodes they create look like this. All right, so it seems like we're going to have to create multiple grids, one per antenna type, so that we can collect all the antinodes for that antenna type. The first example, okay, has antennas with two different frequencies. So the antinodes they create look like this. Okay, so we have our test and our output. Because the topmost A frequency overlaps with a zero frequency antinode, there are 14 total unique locations that contain an antinode within the bounds of the map. Calculate the impact of the signal. How many unique locations within the bound of the map contain an antinode? All right, let's grab our input. And I'm not quite sure how. I would like to be able to print out this map, but I don't know what I'm going to do if two nodes contain an antinode. Because they were saying that because the topmost A frequency overlaps with a zero frequency antinode, there are 14 total. So that one would not render anymore. How do I want to do that? Day 8.part1 input. Let's just do expect results is equal to 14. Over to our package and enable day 8. I must have made that async and forgot to run the tests for it, which means that needs to be 08. Okay, so we've got our structure set up. So I think what we're going to end up doing is creating distinct grids. If I do a private static parse, which takes the input and gives us maybe a dictionary of character to grid of we could do character for now. Let's do antenna, and that's going to have a character associated with it, and then an antinode. So then this could be a grid of nodes. I did read something on Mastodon yesterday, and somebody was talking about some of the solutions for Advent of Code that deal with large grids like this. It ends up being really really expensive to store everything when you could just iterate over the items that actually contain something. So we may need to make a grid that is not just going to allocate, every empty spot. That might be interesting. Something like a loose grid or a lazy grid or something like that. Okay. So let's have an array of character and grid. What I'm wondering here is I already have a way to parse grids, but I think that as soon as I reach I could probably just start off by saying input dot let's reduce the input into a set, and that gives me all the characters, and then guard that the char is not equal to a dot, which was the empty space, else return. That needs to be a set of character. And I need to return, let's do into. Okay, so now we have this. We can now create a grid for each one. Let's see, for char and chars. Okay. So now I should have separate grids for each one. So let's get our grids. We will parse our input. I'm going to print out the grids and then return that. We can run our test again. Okay, our nodes need to be custom string convertible. Empty return dot antenna. Let C return C. And case antinode. Return hash mark. Okay, so A looks like that. I think I need to change the way I print this. Let's see, grids. Okay, so now we have our grids here. I think I put the wrong input into the test. Yeah, I did. We want this input. Distinct characters needs to exclude the empty one. I can't tell if that was a dot. Yeah. That's weird. Shouldn't have 3 values. Oh, it's got a new line. Not charted is white space. Okay. Now we should have our 2 grids for the 0 antennas and the A antennas. Now the antinodes can be its own grid, I think, because if we already have an antinode there, it doesn't count again. But that doesn't really save us any time. So let's do a static func. Yeah, I'm starting to think that this grid isn't going to be super useful because we're going to be iterating over so much empty space for no reason, where we could just iterate over the positions. I think I'm gonna try. Let's copy the grid type, and I'm going to create a new file called a loose grid, not text. .swift. Okay, and then that's going to take that. We can keep the point. All that stuff is fine. And this sendable part can be moved up as well. I'm going to call it a sparse grid, not a loose grid. I think that makes more sense. Import, what do I need? I don't think I need anything. Yeah. Why isn't it highlighting? Let me delete it and re-add it. I think Xcode is being weird. Okay, so instead of there being this element is going to be just positions to elements. We're going to need to know how big the grid is. So these can no longer come from the count. Or from the data, rather. This one is going to end up using the point. So let's do data for point xy equal, or sorry, like that. And then this one, point xy equals new value. Subscript for an element will be empty if we don't have one. That's fine. Then this one is just going to be data point, and data point equals new value, like that. That will also be optional. And this one's going to just take the entire input set. We also need to know width and height. No, rows is height. Calls is width. I think I'm just going to rename those to width. Okay. Is inside still works. Okay, let's do an extension on sparse grid. For this one, instead of doing data.map row, we're going to do for y in height. Yeah, If we have a value for that data, we'll print it. Otherwise, we will print a dot. Yeah, that's exactly what I want. Oh, but this doesn't print. I need a string. Okay. This is pretty nice because now if I just want to get all the points, I can get that. I'm going to call this public private set because you can't change this without modifying those potentially. So I don't think that that's something I want to do. Yeah. Okay, so let's go back over to day 8. This is going to be a sparse grid of nodes. Sparse grid is public. Let's see, we need to compute the position for each one of these, and we won't be using empties at all. Compact map. That'll be guard, let that, else turn nil. So this is where I need to know what number. So this is going to be dot enumerated. Gives us the offset, I think, and the line. Just double check that. Data here is going to be we would have to do reduce into. So if I did point and point to node here, this would be lines.enumerated dot reduce into All right, so we've got a for loop, and now we have the point here is going to be line.offset. Sorry, point. This is going to be c.offset, line.offset. And then the node is going to be node.antenna for that character. And now we can take the accumulated value and assign it. This needs to be c.element. I think I'm going to call this row. And then I'm going to call C column. That needs to be into. Don't need any of this. Okay. All right, so finally, now I have a grid. And that grid only contains one antenna type. So for every combination of antennas, we'll have a difference, and then we can reflect over that vector. Let's see, so how am I going to do... I want to create pairs of all of the different points, every combination. So it's going to end up being something like this. No, not like that. For point A, we're just going to call it A in grid.data. This is not a grid, this is a sparse grid. For B in grid.data.drop first. No, it's going to be okay. So this is going to be like the vector between them, and that's going to be a.key minus b.key, which are the 2 points. I think I only care about the keys at this point, so that I can just do this. Minus can't be done to 2 points. I thought I did add. It seems strange that this is the same thing as multiplying or adding by a negative. But it doesn't know how to do that. If I did star LHS point with some right-hand side double, not double, this just needs to be an int. Okay. Yeah, and I wonder if I get rid of this now, does it know? I feel like it should know. But whatever. Okay, so if I take a minus this vector, this is going to be, I don't know, C and D for possible antinodes. We'll do AN1, and AN2 is B plus vec. And then for each of these, if the grid is inside AN1, then we're going to say new grid for AN1 equals antinode. And then if grid.is inside AN2, new grid AN2 equals antinode. I think I could probably combine these. Let's do filter grid.isInside, which we can do with this. And then we can, for each on that, new grid AN equals antinode. Okay. So for each grid, we start with this, we print it out, and then let's compute the antinode grid. Compute antinodes for grid. And then we're going to print out antinode grid. Yeah, $0.value here. I don't know why it's running all the tests. I just want to run this one. All right. Okay, so for A, that doesn't seem right. Let's step into it. All right, for 0. Oh yeah, I think I was looking at the wrong one. All right, so that's our 0 grid. So A is 5, 2. That's this one. And B is 7, 3, which is this one. So the distance between this one is 1 down and 2 over. So if I go 1 up and 2 over this way, then I should get an antinode at 0, 1, 2, 3, comma 2. I think I need to do B minus A for that to work, but maybe it doesn't matter. Yeah, I think I need to do B minus A because this one is giving us -2, -1. So if I do that, I would have to do plus and minus here. But if I just do B minus A, then those two calculations should be correct. All right, let's see. Let's do this and that. All right, I'm back. Minor coffee emergency. Okay, let's rerun this. This time I'm getting A first, so I'm just going to run it again to get 0 first. Now the vector for B minus A is -4, 3. That's not correct. Or is it? Oh, sorry. Now it's giving me different ones because these aren't in order. Because I'm storing them in a hash. I'm surprised I didn't get the same value the second time through, but let's just double check. So we're looking at this one for A. B is 4, 4. It's 1, 2, 3, 4. That's this one. So that is a difference of, to go from here to here, I need to add 3 to Y and subtract 4, and that's correct. So AN1 is 12 and negative 2. That's not in the grid. AN2 is 0 and 7. That is in the grid. So we should get one about here. That doesn't make sense. Oh, 0, 7. Sorry, that is down here. That does make sense. Okay. So after this one, we should have a new grid. With a hash mark over here. Okay. So now I'm going to take, so for each one of these grids, we're going to map this to the antinode grid. And then from that, we're going to map again to the points. So that's going to be and this is going to be data. And then we're going to reduce that data into a set. I guess we don't need to map to data because this is just going to be grid in. And then we'll say grid, that needs to be the set. Set.insert for each grid item that is an antinode. I kind of want like a search function here for our sparse grid. Where the element is equatable, then should give me an array of points. Filter, yep. Okay, so now we can say search all points. I didn't make that public. Okay, that's why, because these need to be equatable. Can I convert value type set point to expected in out set point? Yeah, so at this point now I can get rid of the this, that, and that. Okay, so that gives us our value here. We're going to say count equals this and do dot count. All right, so that passed. Let's go back over here. Let's grab our puzzle input. And I probably don't want to print all this stuff. It'll make the result much slower. Not the right answer. Your answer is too high. Okay. Let's just run across this again. Antinodes can occur at locations that contain antennas. In this diagram, the lone antenna with frequency capital A creates no antinodes but has a lowercase a frequency antinode at its location. Because the topmost A frequency antenna overlaps with a zero frequency antinode, there are 14 total unique locations that contain an antinode. How many unique locations within the bounds of the map contain an antinode? So we're taking all the grids that we have, reducing them into all antinode points, and inserting them into the set, so we shouldn't have any duplicates. All the antinode points should be inside the grid because we filter it here. I'm going to go back to printing and just step through this input one at a time, I guess. First would be helpful to know how many grids there are. can't do that because I'm in a breakpoint. Or I'm in a breakpoint inside of a closure, I mean. All right, so we've got 48 grids. We've got a grid for E and T. Let's just make sure that these are I'm just making sure that I'm not looking for characters that shouldn't be there. All right, that looks fine. All right, so we're going to just start printing them one at a time. So here's the first one. We've got maybe one here and one here-ish. So that's 2. This one should have one up here. The other one would be off the grid. Then we'd have one around here for these 2. One around here for these 2. That looks correct. This looks correct. That looks correct. This one is from here. These 2 produce this one and that one. And this one produce that one. This looks correct. Okay, let's take a look at another one. These 2 would be off map. This one and this one produce that one. This produces this one. This one and this one would be off map, and I'm guessing that's off map as well. I don't actually need to print out each one anymore, so we can just do that for some smaller output. I must be missing something here. Let me read it again. So this is interesting because I don't know if my solution would handle this properly. I guess the question I have is, what if I had, let's just say that they were in a line. So I have an A dot A dot A. No. Okay, like this. So if I had something like this, then there would be an antinode at the middle one. And at the moment, that would overwrite it. Which is fine, but that means that I suppose that I would have already known. Oh, I'm creating antinodes for where grid.data. Yeah, this definitely needs to be both, because I want to only find elements. If I do a dot value is an antenna. Where case a dot value equals antenna. Can I do that? No. I think maybe I could do the search all. If I did grid dot search all for nodes, but I would be looking for individual. I suppose I don't need the character here. I don't have the character because I'm immediately splitting it into multiple grids, so I don't actually need that. So grid.data where a.value. Oh, but no, I'm only mutating a new grid every time. So I don't think this actually helps me. Where b.value is an antenna and b.key is not equal to a.key. This then is value. No, key. I don't think this changes anything actually. Still getting 328. Also, this messes up my formatting. we're going to do a percent sign. Hey Samuel, how are you? In this diagram, the lone antenna with frequency capital A creates no antinodes but has a lowercase a frequency antinode at its location. Let's just run a test for this one. Good, went to Andover State Park and then won Fortnite with my girlfriend. Nice. I suppose it might be too cold to skate outside. Cold's okay, but all this rain makes it slippery and dangerous. Yeah. It also hurts when you fall in the cold. It hurts more. Okay, so I need to get rid of these so that I can run the results equals day 8 dot part 1 input, and we expect the results to equal 1, 2, 3, 4. Question for you. Does my microphone sound any different than it did yesterday? Because I'm getting kind of this weird ringing effect in my ears. Okay, that test succeeded. I think it sounds the same. Definitely no ringing or anything. Okay, well that's good. Not quite sure what it is. Calculate the impact of the signal. How many unique locations within the bounds of the map contain an antinode? Lowercase letter, uppercase letter, or digit. Is there anything in here that is not that I'm supposed to skip? I don't think so. I guess maybe I'll just recap what I'm doing so far. I take the input for each one of these distinct antenna types. I create a new grid that only contains that. Then we calculate the difference between these two, and then add a node on each side of it, an antinode. And we do that for every combination, every pair of antennas of the same frequency. So for all of our grids, we compute the antinodes for that grid. Computing the antinodes creates a copy of the grid for each A in the grid's data where the A's value is an antenna. Then for each B in the data where B's value is an antenna, but it's different, we compute the vector between the two. Let me just double check my isInside function. Greater than equal to 0. X is less than height? No, that's width. How did that not bite me before? So maybe I was not filtering out enough stuff. Okay, this time through we get what? 331. That's more. Did I say it was too low? No, it's too high. All right, we've got a point. Point.x is greater than 0 and less than the width of our grid. Point.y greater than 0 and less than the height of our grid. Those are initialized. Here. So that should be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yep, 10 there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 by 10. Okay, I think that I could potentially get the wrong answer if I have an extra new line like happened last time. So let me run it. The input here, I need to look at it in a text editor. So we have 50 lines and 50 columns. That's it. Shit. That's annoying. So I think that I had a few examples where things might have been, yep, 323. A few examples where the input was on the edge. All right. After watching over your shoulder as you work, the historians ask you if you took the effects of the resonant harmonics into your calculation. Whoops. After updating your model, it turns out that an antinode occurs at any grid position exactly in line with at least two antennas of the same frequency, regardless of the distance. This means that some of the new antinodes will occur at the position of each antenna, unless that antenna is only one of its frequency. Any grid position exactly in line with at least two antennas. Oh, so it repeats. This means that some of the new antinodes will occur at the position of each antenna, unless okay. So these three T frequency antennas create many antinodes. In fact, the three T frequency antennas are all exactly in line with two antennas, so they are all also antinodes. This brings the total number to 9. The original example has 34. All right, so let's grab a test for part 2. Part 2. Dot. All right, it's going to be pretty similar, but this time we're going to compute the antinodes, and I'm just going to say repeating true so that we can reuse this. And basically I need to say that while we've got our difference, and then starting from A, oh, it doesn't matter which one we do. We just start from A and we'll just continue to walk backwards along that line, adding an antinode at every position while it's inside the grid. So we know we have 2, so we know that antinode position is going to be there while the antinode position is inside the grid. We're going to actually create 2. Do I want to do that? I don't think I need to do it. I don't need 2 variables. Okay, so then we're going to, on the new grid, we're going to set the antinode position equal to antinode. And then we're going to antinode position minus equals the vector. So we're going to keep going that way. And then we're going to set it to B. And this time we're going to add. Minus equals cannot be. That's annoying. kind of strange for this to not just be inferred for me. All right, so for this one, oh, this is going to ruin part one. Here I basically want to say guard repeating. I could do a repeat while is inside point. Antinode position. But this is always going to add it at B's position. Or sorry, at A's position, which I don't want in this case. I suppose I could do it like this. I'm missing something on the Swift plus equals operator. I don't want a custom operator. Okay, this is fine. Plus, yes. I don't want. You can't, let's see. You can't overload the default assignment, sure. Including plus equals, sure. Oh, that's how I do it. In, out. Let me let my dog out. So this one is going to be in-out point. Same thing here. All right, so we'll start with A, and we will mark A as an antinode. Then we'll subtract the vector and just continue until we're off grid. Then we'll start with B, mark B as an antinode, and continue adding. I think that could work. Let's look at our tests here. All right, test succeeded. And then it said if I run the original input, I should get 30 something. 34. Let's see, test part 2 example. We're going to do that, but replace this with the other input from up here. And this one is going to be 34. All right, let's run it. Let's get rid of printing the grids. $1,077. All right, we completed day 8. Nice. All right, let's do a commit. Sources day 6. I did that last time. Test day 6. Let's see, commit, make day 6 async is what I changed there. Then add, I don't know what I did with day 4, but I changed something. Oh, that's just refactoring for this time. This is all basically day 8. Day 8. All right, amazing. Thanks for joining, and we will start on day 9 tomorrow. Have a good Sunday.